unit, okay, but also for of the collection system, the piping, and the fan, and also the electrical part, so to control and to manage the filtration system. All these parts are important in the same way to guarantee the proper performances of a filtration system. This because if we install a good filter unit, but we forgot to design in the proper way the piping, for example, we for sure we will not reach the goal, and we will not satisfy the request of our company. We start talking about from the collection, so the suction hood. First of all, we have to understand which is the request and which is the pollutant to be treated in our system. The first thing we have to understand during the design phase of a filtration, a complete filtration system, is the airflow we have to guarantee to each suction point. So, in order to design the proper airflow, so in cubic meter per hour, we have to first of all understand which is the pollutant, which is the size of the pollutant, the concentration, and which is the geometry of the area that must be treated. For example, we can find an example can be a turning machine, a machine tool. Okay, in this case, the volume can be, for example, completely closed. In this example, it's very easy to calculate the airflow, because probably the co-structure of the machine tool is able to suggest us an airflow, minimum airflow, in order to guarantee the performances in terms of quality inside the machine. Then, with our experience, we can also suggest which is the proper airflow for a volume. In this case, we have only to calculate the volumes per hour that are needed for a kind of volume. Another opportunity, another example can be a free area where there is a pollutant inside. And in this case, we have to design the proper filtration, the proper suction point. We can have two different examples. We can do a very big, like in this small picture, a big suction front, dimension in this case 1 meter per 3 meter, less or more. In this case, we can calculate the minimum airflow. Keep in mind the minimum velocity that we have to guarantee on this area. Just a second, sorry. For example, we use value between 0.4 and 0.6 meter per second for a suction hood like this. These are good. This solution is good when we are talking with aeriforms, so with very small particle, like example for VOC, or very small dust, like in the welding fumes and so on. If we have instead metallic powder, or from very different kind of metallic operation, we have to design instead very small suction point, closest as possible to the point where the pollutant is produced. In this case, we have to guarantee very high speed close to the site of production of the dust, with velocity between 15 and 20 meters per second. This because due to the weight of the pollutant. If the pollutant, like the powder of steel, his weight is high, we need very high velocity. And the third thing is the volume confinement. So it's very, very important to guarantee negative pressure in the area where we install a suction point. This because with the negative pressure in the area, we are quite sure that the pollutant don't go outside this area and is collected in a short time from the filtration system. If we are not able to guarantee this, we are not sure if the pollutant will be catched or not. And this is an issue because if we are not sure of this, we are not sure that the system will work properly. This is a recap in order to understand what can happen if we undersize or oversize the system. So, because it's easy to understand that if we undersize the volume or the airflow, we will for sure we will have a problem. The airflow is too low, the pollutant will be not collected in an efficient way, and the pollutant for sure will be accumulated and dispersed in the environment. So we will not reach the goal, and our customer will be not so happy. But also an oversizing of the system can be a problem. This because probably, but not for sure, we will have a good collection because we will have a very high airflow rate and very high speed of the air, so the collection probably will be good. But in terms of plant oversizing, so high cost of installation, high running cost, and high cost in terms of energy due to the kilowatt consumption of the electrical motor. And the third thing is if the confinement is not made in the proper way. In this case, we can probably design the good volumes in terms of airflow and in terms of speed of the air on the suction front, but with a bad confinement, we will not reach our goal. This means that we will have to oversize all the plant, and we will have again high cost in terms of installation, running cost, and so on. Okay. If you have any kind of question, you can stop me, and I and Saverio can try to answer to your question. Okay. The second very important thing in the design of a filtration system is the piping. So all the tubes between the collecting point, so the suction point, to the filter and the exhaust of to the chimney. The pipe is important because make possible the transport of the pollutant from the suction point to the filter. In order to properly design the piping, we have first of all understand which is the pollutant. So if you are talking about dust, dry smokes, oil, VOC, and so on, we have to understand the pollutant particle size. If we are talking about of millimetric dust, or we are talking about micrometric dust, for example, the specific weight, because it's easy to understand that steel is heavier than, for example, glass, or it's heavier than oil. And the abrasiveness index of the material. In the here below, we can see some example. Iron powder from machining operation. We have medium abrasiveness, and in this case, we can suggest a speed between 18 and 22 meters per second. This because we have to guarantee to avoid any accumulation of material inside the piping due to the high specific weight of the pollutant. A different example can be the oil mist. Oil mist is light compared to the iron powder, no abrasiveness, and the velocity must not be so high. We can reach a good value between 14 and 16 meters per second. Another interesting example can be the glass powder. Glass is extremely abrasive. This means that we reach a media between the necessity of to avoid the accumulation, so high speed, and the abrasiveness on the piping, so low speed. For this kind of pollutant, we suggest speed between 16, 17, or 18 meters per second, no more. Here, a very simple, I hope a very simple formula in order to calculate the diameter, the proper diameter of the piping. For round piping, it's easy. It's easy. We have only to apply this formula. So this means that knowing the airflow, the necessary airflow rate, and the speed of the air we want to in the piping, we apply this and we calculate the proper diameter. If we use rectangular piping, we have to keep in consideration that there are some edge effects in the piping if the ratio between A and B is not close to 1. This means if the pipe is very rectangular. In this case, we have to adjust the formula with keeping in mind this difference, and we have to calculate the hydraulic diameter, so dA, in order to design in the proper way the diameter of the piping. But it's like the same. Then we have also to define which is the material and which is the piping thickness necessary for the application. Again, we have to understand the particle size, the specific weight of the pollutant, and so on. We can use different material in different thickness depending from the application. For example, in an oil mist application, we don't need the very high thickness of piping because it's not necessary, but we will use a specific gasket for oil in order to avoid any kind of leakage. In case of very abrasive material like glass or like, I don't know, steel, stainless steel material and so on, we will use higher thickness or special material like Ardox, Creusabro, and so on that are with an increased resistance to the abrasiveness. On the other hand, using this material, we will have high cost and difficulty on during assembly phase because the use of this kind of material is more difficult compared to the galvanized steel, for example. And here you can see which are the typical kind of piping we use in our system, starting from galvanized steel piping with spiral construction to the flanged one, so galvanized steel but with flange, stainless steel piping, plastic piping, and so on. So from my point of view, but I think Saverio can suggest the same, we usually suggest to not use for dust but also for oil spiral galvanized piping. This because the leakage, the sealing is not guaranteed, and the risk of leakage or damage is very high due to the construction form. We use stainless steel piping or plastic piping when the pollutants are acid, for example, or the VOC is corrosive on the carbon steel. Instead, we use painted carbon steel piping or painted hard steel piping when the material is very abrasive and we need to reduce the risk of damage to the piping. And the last but not least for the piping design is the geometry of the piping. So we have to keep in mind the bend radius, the number of bend sector, branches, the shutter position in the in the plant, in order to guarantee the functioning and the proper balancing of all the system. And this characteristic of the piping must be designed, but must be keep in mind during the design phase. Otherwise, when we will start up the system, we will some problem can for sure occur. So, what can happen if we oversize or undersize the piping? If we oversize the piping, we will have air speed in the piping very low, and this means that we have the risk to accumulate pollutant inside the piping. This is a risk not only because we are not able to work the system properly, but also because we can risk to damage the piping, and the piping can also can be also completely clogged, so we cannot guarantee the performances of the system. On the other hand, we can also undersize the piping. In this way, we will have for sure high speed in the piping, because the piping will be very small, but we will have also very high energy consumption in terms of kilowatt of the ventilator, and piping wearing, so wearness. Okay. If we choose the wrong material or the wrong thickness, we can go through metal corrosion in case of acid or critical pollutant, and we can risk to damage the piping. Again, if we don't choose the proper piping geometry, we can find a very high pressure drop. So this means very high power consumption, or on the other hand, bad performances, because we are not able to guarantee the performances of the plant. Saverio, do you want to add something? No. Okay, we can go ahead. The third part, to design a proper filtration.
Fede, sorry, Günther here.
Yes.
My guy has a question.
Okay.
In the earlier page, please.
Which page?
In the piping page, which we
Okay.
have.
Okay, just a second.
Back.
Yeah, here, stop.
Okay.
No, one ahead.
Head, this one.
This one.
Yes.
Okay.
What you mean with early wear in indicate material thickness?
This means that if the material is abrasive, we can the thickness of the piping can be reduced during the time. Okay. This means that we have to oversize the thickness to reduce the risk to create holes inside the piping.
Okay, thank you.
Okay.
Okay, if we are just with the questions or by the questions, can you please go back to the capture, just
Yes.
to the very beginning?
Absolutely. Okay, this one?
This one, yeah?
Okay, tell me.
Metallic powder with high grain size velocity between 15 and 20 meters per second.
Yeah.
Do you mean 15 to 20 meters per second at the square? At the square surface? No.
This means that a suction hood like this in the picture probably is not a good way to collect this kind of powder. So we don't suggest to use a suction hood like this, but we suggest to do a small suction hood close to the site of production of the dust.
Okay, I understand.
In this way,
then increase the velocity. No?
yeah. So we have a piping with, for example, 20 meter per second of the high speed, and we put the piping very close to the site of production in order to collect the heavier parts.
Okay.
Just for example, like the suction arm for the welding application.
Yeah, okay. Thank you, understood.
Okay. Okay, we start talking about the design of the ID fan. So the fan, the blower, is one of the most important item in a plant, in a filtration plant, because this guarantee the airflow. So usually we have at least two very important characteristics that must be for sure guaranteed: the emission, so and the airflow rate. The emission are guaranteed by the filtration unit, so we have to choose the proper filtration unit, and the airflow rate is guaranteed by the proper design of the ID fan. Okay. In order to design in the right way the ID fan, we need some preliminary information. For example, the fluid temperature, the working condition of the plant. So if we have only one condition, or for example more condition with different airflow in different period of operation, we need to know the exact plant and piping geometry, and we need to know which kind of filter unit will be installed in this system. With all these, we collect this information in order to calculate the total pressure drop of the system, keeping in mind not only the filter unit, but also the piping, the collection system, the chimney, and so on. With the information of the pressure drop, we can select the proper ID fan. So we can study the characteristic chart of the ventilator, and we choose the one that guarantees our performance. Then we can choose the fan configuration, so the optional and the size, the orientation, and so on. And then at the end, we have to choose the proper electrical motor, because the system is made of a lot of items, and all these items must work together in order to guarantee the performances. So first of all, we already collected the information, and we can start to calculate the pressure drop of the system. The total pressure drop are composed by two different values. The distributed pressure drop made by the straight piping, so is the summary of all the straight piping. It can be calculated with some very complicated formula like this, but this is my job and this is our job. So if you need it, you can ask us. This parameter keep in consideration the material, the speed of the air, the density of the air, what happened inside the piping. So a lot of parameters, and it's a little bit too complicated in order to explain today. And then we have also the summary of the local pressure drop. So this means all the band, the connection, but also the filter unit, the suction hood, and so on. By the summary of all these parameters, we can calculate the total pressure drop of the system. With this value, we can reach the characteristic chart of an ID fan, and we can try to understand if the fan is good for our system or not. First of all, we have to understand this is, for example, the characteristic chart of our pulsatron with the cartridges. But we can see, first of all, we have to understand the rotation per minute of the fan at which the curve, the characteristic chart is calculated. We can see different line in this graph. This is the blue one. This one is the static pressure that the fan is able to guarantee. The black one is the total pressure, but it is not so important for us, this value. Here below we have the dynamic pressure. Again, this is not so important for us. Then we have the efficiency, and it's very important. The power consumption of the impeller of the fan, and is a very important parameter, and the sound pressure level of the fan, the green one. Okay, so I can try to explain this with an example. For example, we calculated that for our filtration system, we need 3,000 cubic meter with at least 2,050 Pascal of pressure drop. So we asked to our supplier of ventilator, and he suggests this one. We see that at 3,000 cubic meter, we have at least 2,800 Pascal of static pressure. This means that can be good for us. We understood that this fan is working at 3,000 meter per rotation per minute, so 2 poles motor. We have to understand also if it's working in a good area or not. So we have to understand its efficiency. As we can see, here we are at the maximum efficiency of the impeller. So this means that we are choosing the proper fan because it's at the top of the efficiency curve. We have also to see which can be, in the green line, the sound pressure level in this condition. So for example, 73 dBA. And which is the power consumption. The power consumption of the impeller is, in this case, less or more 3.5 kilowatt. This means that we will have to install at least 4 kilowatt motor. Then we understood that this can be a good fan. We have to configure this, choosing all the item and accessories that will be define the fan. The type of material, again, we can do it in carbon steel, in stainless steel, or in plastic with the stainless steel impeller, for example, depending from the pollutant and also from the temperature. The outlet direction, as we can see in this picture, we have some ventilator with the outlet direction vertical or inclinated by 45 degree or by 0 degree and so on. This depends from the design of the plant. Then we have to choose the type of coupling, so the connection between the motor and the impeller. The easiest way, like in the last picture, this one, is the direct coupling, so the direct connection of the impeller on the shaft of the motor. This is the easiest way because it's the most economic one, and this is good in most of the cases. But sometimes we need more than this for different reasons. For example, we can do a coupling like in this picture with not a, so this is not a direct coupling, but between the motor and the fan and the impeller are installed some bearing in order to disconnect the impeller and the motor. In a third case can be to use not only a bearing system, but also, like in this picture, a connection between, I don't remember in English, between a chain between the motor and the bearing shaft. Why we should choose this kind of connection? For example, we can choose a connection like this or this one for maintenance. In this way, if we install a bearing shaft, we can disconnect the impeller, or we can change the motor without dismantling or the fan. In the easiest way, so with a direct coupling between the motor and the impeller, if we want to change the motor because, for example, it's broken, we have to dismantle also the impeller of the blower. Okay, but then we have to understand if we need a variable speed drive, so a variable frequency drive, if we need a silencer due to the sound pressure level required by the customer, and if the area is ATEX classified or not. With all this information, we can choose the proper fan configuration and the proper fan for our system, the proper blower. Last but not least, again, we can, sorry? No, so we can choose the proper electrical motor.
Ah, somebody need to send him. Yes?
Okay.
I will do. Evo šaljem ti link. Ajde.
Sorry, Giovanna?
Yeah?
Okay, I don't understand, sorry.
Oh, sorry.
Okay, don't worry. So we are talking about electrical motor configuration. We already designed the blower. We need to choose the proper motor that must work together with the blower in order to guarantee the performances. First of all, we have to understand the rated power. So the power that the motor can supply to the impeller, and this value must be higher than the power consumption of the impeller. So for example, we see that we already saw that for this for our example, we need 3.5 kilowatt, less or more. Yes. We will install a motor of at least 4 kilowatt. Then we have to choose the proper number of poles of the motor, because related to the poles is the RPM, so the rotation per minute of the shaft of the motor. We need, for our example, 3,000 rotation per minute. We will need a 2-pole motor. It's very easy. Then we have to choose the form factor. As you can see in these two pictures, this is this motor is a Siemens with the form factor B5. So the motor is flanged to the fan through this flange. This other motor is exactly the same size, but is not flanged to the fan, but is a connection to the structure of the fan with this foot. Okay, then we have to choose the proper voltage and the frequency of the motor. In Europe, in Italy, for at least, we use 400 volts, 3 phases at the 50 hertz. But if we install a motor in, for example, England, we need a different voltage. In USA, we need a different voltage, and also need a different frequency. So we have only to choose the proper one for the installation. Then we have to define which is the efficiency we need. So sometimes we need an efficiency in class EA2, sometimes EA3, and in the future EA4. Now for our policy, we install quite ever at least EA3 in order to guarantee optimal performances in terms of power consumption of kilowatt.
Maybe Federico, it's important to remark the difference between the kilowatt installed and absorbed.
Yeah, it's very important. Very often happen that our customer asks us why we wrote in our offer, for example, kilowatt absorbed, I don't know, 11, kilowatt installed 15. This value. This because if we see the chart, the characteristic chart of the fan, we see that at different point. So I try to explain. The fan, the blower is able to guarantee the performances all through all this line. This means that he's able to, at the same time, he can do 2,000 cubic meter with 3000 Pascal, or 5,000 cubic meter with 800 Pascal of static pressure. In different condition, he will ask different power to the motor. In the first case, he will absorb less or more 2 kilowatt. In the second point, the power consumption will be close to 4 kilowatt. When we design the motor, we must be sure that in all the possible conditions, the power consumption will be always lower than the rated power of the motor. This because we cannot have the risk of power consumption higher than the rated motor, because in this way the motor will be for sure damaged. Sorry?
And when there is a margin between absorbed and installed, when we change the frequency, thanks to the inverter, we can upgrade the airflow.
In case, if necessary, if we have margin, we can, with installing a variable frequency drive, we can increase the performance of the fan, because I try to explain with the characteristic chart, increasing the rotation speed of the motor, so of the blower, we can move up the static pressure, the HST, the static pressure line. So we can move it up, so we can guarantee more performances in terms of both airflow and static pressure.
Yeah, exactly. If there isn't this range, we can't do nothing.
We can do it, we cannot do it, and in order to reach more performances, we not only we have to install an inverter, so a variable speed drive, but we have also to change the motor, and sometimes the different motor, so a bigger motor, need also a different impeller, because the connection is not always the same. Okay, if you don't have any other question, I can end the part of related to the blower. So, undersizing a fan, for sure we will not able to guarantee the design airflow of the filtration system. Probably we will not able to collect in the proper way the pollutant, and if we design the piping in the right way, but not the same for the blower, we risk the accumulation of the pollutant inside the piping. On the other hand, if we oversize the fan, the blower, we will reach very high speed in the piping, so we risk to damage the piping, and we will have for sure very high power consumption, because we need more energy to make the same result. Another very important risk is to work out of range of the fan. What does it mean? I try back to the slide of the characteristic chart. As you can see, the line starts from this point and end to this point. This means that the constructor of the blower suggests us to not work in this area, and also to not work in this other area. This because, first of all, the efficiency is very low. As you can see, the efficiency fall down. So it suggests to work, in this case, between 250,000 and 4,000 cubic meters, less or more. But also working in the first area, so with very low airflow, we can have a risk of vibration and also the damaging of the impeller, because it's not a working area for the blower. This is a very important thing to keep in our mind. So bad performances, risk of vibration, and with the very low efficiency means very high power consumption. Then we can also undersize or oversize the electrical motor. If we oversize the electrical motor, we don't have any risk. We spend only money. But if we undersize the electrical motor, it's a big issue, because not only we are not able to guarantee the design performance, but also we are not able probably to work the system, because if the power consumption, like Saverio said before, is higher than the rated power of the electrical motor, the motor will be broken in a few times. This means that we have to stop the system and we change the motor. Okay, and the last part of the system unit, of the complete system unit, is the filtration unit. We already talked about this in the previous webinar, so I don't want to spend more words on this. However, we already designed the collection system. We made the piping in the proper way. Now we understood the pollutant and the service type and so on. So we have only to choose the proper filtration system in order to guarantee the outlet concentration required by the customer. This means that we have only to choose the proper filtration unit. This is an example in the picture of a big filtration unit on oil mist. There were, if I remember well, 36 machine tools with less or more 70 suction point. It's a very long piping, because this branch is for less or more 40 meters. This means that it's a very long piping. We installed in this case an MCOS, so that worked properly with oil mist. The airflow in this case was about 200 to 28,000, if I remember well, cubic meter per hour. And we installed a fan of 45 kilowatt. But it's just an example. Do you have any question? Yes.
The filter was which size? Going back to the page before. This
okay.
Filter.
This is a. Sorry, Gunther, I don't understand you.
It was
the MC.
Okay, this is an MCOS with 7 modules. So it's made of for 28,000 cubic meter per hour. Is a double stage filter. I don't know if you know it, but it's a double stage filter. So we have a coalescence filter, a first stage, and then a second stage with 2 different kind of coalescence filter inside, with the optional to install also an HEPA filter, an absolute filter, if you need to put the air inside again the building. But this was not the case. The length
14.
14,
right?
yes, is 5 meter length, less or more.
Yeah, MCOS 14.
Okay.
Federico, I would like to remark that for this reason we speak about air filtration systems, because all component is very important for the final result.
Absolutely, absolutely, Saverio. What I want to explain you with this webinar is exactly this. We can choose the best filtration unit, so the best HFiltration filtration unit, but if we don't design in the proper way all the item in the system, the filter will not work, and we will not reach the goal of our installation. The same if we install the best piping and so on, but we don't choose the proper filtration unit, the result will be the same. So it's very important to don't forget all the part that made the system.
Before to stop the pollution inside the mist collector or dust collector, we must to catch. And after this step, we must to transport the pollution from the suction point to the filtration unit. For this reason, I would like to remark that we speak about filtration system. But often everybody try to, the focus is just the dust collector or the filtration unit, but there is something more. Okay.
Yeah, and I want to add this. Very often, some our partner or some of our customer call us and tell us, hey, there is a problem on this filter. This filter doesn't work, and sometimes is due to the filter, but very often is not due to the filter, but due to, for example, the piping or the blower or the collecting unit. So we have when there is a problem in the plant, we have to investigate in order to understand where is the problem and why there is a problem.
Yeah, I have one example very clear. Often we receive some inquiry or call, and we speak about the dust collector in ATEX version, but nobody take care attention to the duct net when we speak about explosion dust, when we play with explosion dust. In order to provide the right systems, we need to speak about the dust collectors, but also the no-return valves. For this reason, it's very important to speak about air filtration system and not just about some components.
Fede, I still have one question.
Tell me, Gunter.
It's a very simple question, simple answer. You have, in the very beginning of calculating the pressure drop, you have shown us wonderful formulas. Yeah.
Okay.
So we here at FIROC, we are using, let's say in average, the pressure drop of the filter PC back or the pulsatron of 800 Pascal.
It's a good value because, for example, for our pulsatron compact, we set the cleaning system, the automatic cleaning system with the pressure drop, so the DP control, in an interval between 600 to 800 Pascal. This means that the system starts at 800 Pascal, the cleaning, and stop the cleaning at 600 Pascal. If the system works in the good way, for the lifetime of the cartridges, the filter will remain always between 600 to 800 Pascal, and your value is correct. When
the running value of the pressure drops is correct, yes.
Yeah. If you are talking about, for example, bag filter, we suggest higher value between 800 to 1000 or less or more Pascal. It depends from case by case.
Oh, okay, I understand.
But your value is correct. It is not wrong.
That is the most important thing. Not wrong. Okay.
Yeah.
It's not wrong, yes.
This means that in the first period of the working time, the pressure drop will be lower and the performances will be higher than the design. And when the cartridge will reach their nominal pressure drop close to 800 Pascal, you will have the good performances. So it's the good way to design the filtration system.
Okay. And if we increase, for example, the what to say, yeah, it's logic. Sometimes we are running the filter, the pulsatron, for example, at one customer I can remember, at 1200.
Okay.
But then I have to calculate this in my.
You should. We have to do some assumption. If we are working with a direct coupling ventilator, direct coupling blower, without a variable speed drive, this means that we have to on the characteristic chart of the fan, and we have to understand which can be the performance of the fan with a different pressure drop. I try to explain it with the chart. For example, before we talk about 3,000 cubic meter, and 3,000 cubic meter, the fan will be able to guarantee 2,700 less or more. Less or more 700 Pascal. If the pulsatron, in this case, increase is a pressure drop of 400 Pascal between 800 and 1,200, okay, Pascal, this means that the ventilator will be in the same condition, supply 400 Pascal more. As you can see, this means that the blower should work less or more here.
Yeah.
Okay, but this is not the truth, because here it will able the blower will be supply less or more 1,000 cubic meter, yeah. And you should recalculate the pressure drop of all the system, so the piping, the collecting point, and also of the pulsatron, with 1,000 cubic meter, not with the 3,000 cubic meter. This means that for sure the working condition will be in between the first point and the second point. You should calculate this. You should. It's an iterative calculation. We do it. So this means that you have to calculate the new pressure drop of the whole system, and you will find a new point in the characteristic chart of the fan.
Yeah, okay, understood.
Okay.
Thank you.
If you don't have any other question, I go ahead with the case history in order to end the webinar. So what we can show now is the case history of, sorry guys, okay. Just a second. Okay, this is an installed plant in Switzerland. The customer is a producer of silicon carbide graphite. So he worked with silicon carbide powder, and when we arrived to the customer, there were a lot of pollutant in the environment. The situation was very critical, and we find a lot of issue to be solved. First of all, high concentration of the dust in all the environment and not only close to the working area. An extremely abrasive powder. This because the silicon carbide is used, for example, in the machine tool to work the steel, so it's very, very abrasive. A very big volume. We will see a video after, and a very big volume to be treated. A very small area for the filter installation, and at the end, very low pollutant concentration values required by the customer. So he asked less than 2 milligram per normal cubic meter to the chimney. What we made? We starting from the filter unit, so we choose an HJL, so an industrial version of the cartridge system, but a cartridge filter. We design a new piping line with a lot of suction point like this. We used very piping, so we installed the hose piping of high thickness. So the thickness is, I think, 15 millimeter for this piping, for this blue piping, and is made just for very abrasive material. We redesign all the collecting piping on the existing suction hood, and we also made an environmental cleaning with very big hoods in the roof of the building. We will see it in the video. This is the filter we chose. Is a cartridge filter, but made of high thickness of carbon steel. We choose also a very big ID fan, if I remember well, 75 kilowatt installed. I don't remember if 55 or 75 kilowatt installed for 55. Okay, yeah. For 5,000 less or more cubic meter of airflow. All the piping were in carbon steel with the thickness of 3 or 4 millimeter, and somewhere we installed also Hardox, so very hard material, very hard steel. This is, I try to show you the video. This is the raw material that is treated in this company. And this is the area, a working area. Here we can see some operation, and we see a lot of dust in the environment. As you can see, the material handling of this powder is very complicated, so it was very critical, the situation inside the working area. Our filtration unit with the blower. This is the a general P&I of the installation. So what we made. And it is the suction hood for the environmental cleaning at the on the roof. As you can see in this picture, the situation is really different before and after. So with the proper airflow designed for the volume, less or more 30,000 cubic meter only for this volume, the situation is completely changed.
The customer is very happy because the invoice is already paid. So this is the proof.
Okay, we ended the webinar. We are at your disposal for any question. If we want to go inside any aspect.
Okay. So, any question?
Not at the moment, but we will think about it, and then we will
keep in touch.
Same thing I said, wonderful.
Like always, keep in touch. I would like to invite everyone for the last webinar tomorrow, and the same time like today's. And tomorrow we speak about Industrial 4.0, integrate in the air filtration systems.
In English, not in Polish.
Part in Polish, part in Afrikaans, part English, Italian. We share all language, okay?
Okay.
And the last point, I would like to say something about the nice T-shirt. I speak about Richard. Thank you very much, because your T-shirt is very beautiful. Good. Thank you very much. Thank you very much. Okay. Thank you very much. Keep in touch. And we are waiting tomorrow.
Thank you, Federico. Ciao.
Thank you, guys. Thank you.
Ciao, ciao.
Bye.
Ciao, ciao.
Ciao, ciao.
Thank you. Bye.
Super. Super. Tomorrow is Friday. Tomorrow is the last meeting. We are waiting the beer, German beer.
The Weizenbier.
Yeah. You offer the beer to everyone, Don't forget
Some
it.
people send it by email then.
Yeah. We are waiting with a huge quantity of beer tomorrow. Ciao, ciao.
Ciao. Ciao, thank you very much. Grazie mille.
Das war
Nada,